All right, so let's take a look at, on the class notes, number 5. Right? And we'll look at, let's look at the second one. So we start off with an enolate. Right? We start off with an enolate. So presumably that would have been deprotonated at some point with a base. Base has got to be strong, right? So something like LDA or OH minus, it's got to be a pretty strong base. H minus? H minus, usually hydride won't be that good of a good enough base to deprotonate an alpha CH. It doesn't usually do that. Yep, it doesn't usually do that. So we're doing this one for number 2 there. So the second one on number 5. So here we go. We have our enolate alpha carbon. All right, the alpha carbon here is nucleophilic. Which part of the aldehyde is electrophilic? The carbon of the carbonyl. All right, the carbon of the carbonyl. Also notice here, does this aldehyde even have any alpha CHs? No. Is this an alpha CH? No. Alpha CH means it has to be in the alpha carbon. Now, there is an alpha carbon here, but this alpha carbon has 1, 2, 3 bonds to carbon. There's no alpha CHs. Right? If there's no alpha CHs, can you deprotonate an alpha CH? No, if it's not there, you can't do anything with it, right? So we do our first addition, right? Just like we've done before. We do our addition. Of course, somebody should at this point say, hey, number your carbons. Thank you. All right? So we formed a bond between which 2 carbons now? 3 and 4. So there's 1, 2, 3. There's a bond to 4. What else is 4 was bonded to an H. Okay. 4 had the oxygen, now it's an O minus. There's also this tert butyl group off 4. Right? There's also that off 4. And let's not forget, now we have a tetrahedral intermediate, right? So tetrahedral intermediate, we ask ourselves, are there any good leaving groups? Are there any good leaving groups? No. So we're done then, right? So let's go to step 2. What was step 2? Step 2 was H+. Okay, well what do you think is going to grab the H+? The O minus, very good. Now, this one I told you, right? I told you the product. I told you it was this. So what had to happen? If I number the carbons in the product, it's 1, 2, 3, 4. We had to do what? We had to form a? We had to form what? A pi bond? Where? That's right. Well, okay, that's interesting. So when we say H+ is around, right? Usually there's a lot of H+. There's more than one equivalent. Right? I could have been a little more clear here and said, right, there's a lot of H+ around. Or I could have said H+ is a catalyst perhaps, or just as a lot of it. So let's pretend there's another molecule of H+ around. Where do you think that H+ is going to go? Not the carbonyl. The alcohol, right? Remember when we activated alcohols? Yeah. Oh, no. Well, I told you what the product is, right? What do we need to do? We need to activate that alcohol to form a pi bond, right? I told you the product. So the alcohol is going to be the one that leads to, alcohol getting protonated is the one that's going to lead to a product. So the alcohol gets protonated. So what does that give us? Remember here, 1, 2, 3, 4. These are all, yep, these are all reversible arrows. But I told you the product. So you're always going, so you know where you're trying to get to. On the test, you should usually have equilibrium arrows, yes. I haven't been too hard on people about that, but.
That's not good.
Right, so now what have we done? We've essentially activated this alcohol. And Now is that a good leaving group? It's a great leaving group. And are alpha hydrogens still acidic? Let's look at what carbon do you think has the alpha hydrogens that are acidic? Carbon 3 does. So what if we have these electrons leave their attack between 3 and 4, and the water leaves? What do we end up with? Our product and H plus reformed, right? The catalyst reformed. So that's called an aldol condensation, right? We're losing water. It's a condensation. You can do this in both acidic or basic conditions. So this is in acidic conditions we did this. We did this in acidic conditions. Somebody should be asking, well, what's the driving force? Why would this want to happen? Why would this happen? What's so great about the final product? It's conjugated, right? Because it's conjugated, it can do resonance, right? Do we want to make pi bonds next to each other? Absolutely. So conjugation is the key here. Right? Conjugation is the key here. Now, in your homework, they're going to show it to you in a different way. So this was acidic, right? This was done with acid. Let me show you how it can be done with basic conditions, right? So here, right, we have acid, right? So this is acidic, right, in second step. But you also could do this without any acid, and just in one step, if you heat it up a little bit and force the conditions. Right? So you'll notice in your sapling homework, I think 10 or 11 says OH minus and heat. So let's take this, let's do the exact same, let's get to the same intermediate. Let's say I took OH minus, and I had the same exact starting materials. OH minus is going to take the H from the ketone, right? 1, 2, 3, 4. I can put the aldehyde in there because does the aldehyde have any alpha CHs at all? No. Nope, so it won't hurt it. So what have I made? I made the same exact ketone.
You're just showing like
I'm showing it all now like from start with just basic conditions. From the start with basic stuff. Instead of starting with the enolate, I'm going to get to the same exact starting point, right? So I'm just basically showing even more clearly how this all started. Right? In the practice problems I gave you, it was already the enolate. It was already had a minus charge in the carbon or this enolate, right? This enolate and this structure right here are resonance structures, right? Yep. Everybody see that? Mm-hmm. That this enolate and this up here are resonance structures. So the same steps go forward, right? I can draw them for you again, right? This method, you do an addition, 3 arrows. Tighten this guy up again. So what's that going to give me? It's going to give me that same structure I had. So the same exact intermediate I had before. Yes? Same intermediate I had before. But I forgot to leave out one. I left out one thing. When this OH minus attacked right here, what did it form? What happened to that OH minus? What did it form? It formed water, right? So water has actually been along for the ride the whole time, right? Right, water was in here the whole time. So can that O minus take that, if I force the conditions a little bit, heat it up a little bit, can that O minus take this H? Oh yeah. Good. So this is under basic conditions. So now I've regenerated OH minus, right? Are there still alpha CHs that are acidic? Yes? I could take this and eliminate and kick out OH minus. You can do that. Under heat, right, there's going to have to be some heat. forcing conditions, you can get to the exact same product with water and then OH minus. So in this case, OH minus is like a catalyst. It is weird. They can go OH minus, but we're in OH. We're using OH minus. OH minus is already in there, right? OH minus is not a good leaving group, but we already have OH minus floating around. So it's just like regenerating. That's why it takes a little bit of heat to make this work. Now your book, right? If you had to classify this reaction right here, how would you classify it? What kind of reaction was this? What did we form? We formed from here, right? From this step to this step, what did we form? We formed a pi bond. So what kind of a reaction was it? What kind of elimination? Elimination E2, right? It was all in one step in E2, right? It was an E2, right? It's an E2 reaction. Now your book, now there's a debate about this. Your book says it should be an E1CB reaction. E1CB. I'm telling you E2 is fine. If you take advanced organic, I will show you all the wonders of E1CB and the experiments you could run to figure out what it is. It's actually up for debate. A guy, a professor at Carleton, actually did studies on this, whether or not it's E1CB or E2. Let's just pretend, I think he said it was E2, so I'm saying it's E2. So E2 reaction here, right? It's an E2 reaction. Questions on this, whether using basic or acidic conditions. Is that okay? Everybody okay with that? Okay, so looking at class notes, we're still doing class notes. Number 5, we're going to look at number 3 from our class notes. These are the class notes from 4, 15, 15. So the third one, again, we're already starting with an enolate. And we're going to react it with, this time, an ester. So this is a little different, because esters have, right, attached to the carbon of their carbonyl, a group that can leave. So let's see. So we attack the carbon of the carbonyl. We form a tetrahedral intermediate. I would, of course, number my carbons here if I were you. Just saying. I'm an old pro at this. So now what do we have? We have a tetrahedral intermediate, right? See the tetrahedral intermediate? What do we ask ourselves when we have a tetrahedral intermediate? What's the best leaving group? Or is there a leaving group? So is there a leaving group even here? Yes. And now we say, how many are there? It's just one, so that's the one. But we should always think about the best one too. So the electrons come down. Kick that out. If you look, this is actually the product we're trying to get to. And for some reason, it should just be, after the second step, you'll make methanol. For some reason, it said H2O. I don't know why I did that. But this is the final product you'd get. So with an ester, right, an enolate attacks it, and then you actually form a ketone as a result. And you're done at this point. All right, let's take a look at number 16 in sapling. So we have here, we have an aldehyde and a ketone in the same molecule. Aldehyde and ketone, the same molecule. Now if you look, they're not right next to each other, right? There's no alpha carbon that they're sharing. Remember, sometimes you see the dicarbonyls and they share and we think, oh, that's really acidic. What else is in here? There is NaOH, right, which is a strong base. And they're saying water, the solvent, and they're also saying heat. If you see heat, what should you think about? You should think about maybe there's going to be a condensation, right? An elimination of water at some point, right? If I see that heat, whether it's acid or base conditions with these, with an aldehyde and ketone, I should think about, right? I should probably think an elimination might be happening. Okay. First things first, let's do what? Number our carbons. Very good. I'm glad you guys are all on the same page. So we have I numbered 1, 2, 3, 4, 5, 6, right? So who remembers, we have a strong base, and so what have we been looking for here? What's the first step in all these? We've been generating enolates, right, with all of these. Which carbons have alpha? What alpha CHs do you think we're gonna? What alpha CHs can we deprotonate? What's available to us? 2 and 4. What about 5? But aldehydes are more reactive than ketones. But it doesn't have any alpha CHs. If it doesn't have any alpha CHs, it doesn't matter. But now be careful. Now we have between 2 and 4. So if I see these two things in a ring, right? You've been doing intermolecular reactions. This looks like to me it's going to be an intramolecular reaction, right? So the ketone is probably going to have to be the nucleophile part, and the aldehyde is going to have to be the electrophile part. Now be careful. So if I might be making a ring here. I'm going to be making a ring. Which size rings are good for organic chemistry? 6 or 5? Is 3? Well, let's take a look. So from carbon 4, if I put a negative charge on carbon 4, that's 1, 2, 3. That'd make a 3-membered ring. Is that okay? No. What about from carbon 2? It would be 1, 2, 3, 4, 5. Reasonable. Right? So let's do that. Let's take the H off of carbon 2. And generate that enolate. I'm just going to leave the negative charge on carbon 2 this time. And of course, that's the same as the enolate we normally see. Number our carbons: 1, 2, 3, 4, 5, 6. All right? So which bond do we need to make? So carbon 2 is my nucleophile. What carbon's my electrophile? Carbon 6. All right. So I do an addition. I'm going to make a tetrahedral intermediate. We've already counted this out, so I'm going to make it easy on myself. I'm just going to make a 5-membered ring. But because I've done such a good job numbering my carbons, it'll be just fine. Right? So I can arbitrarily decide, okay, this is carbon 2, this is 3, 4, 5, 6. Carbon 2 is still attached to carbon 1, so that's out here. That'd be 1. Let's see, carbon 3 had a ketone on it, so that's there. 4 doesn't have anything. 5 has 2 methyls. 6 would have the O- and an H. Don't forget, in that first step, what did we form? We also made WADA, that first step. Everybody with me so far? How to make that? Numbering your carbons makes this a lot easier. Just saying. All right. So now we have a tetrahedral intermediate. What do we ask ourselves when we have a tetrahedral intermediate? Is there a leaving group? Is there a leaving group? No. So what am I going to do? Right? We also remember back to our clue about this heat. Right? There's water is going to be a product maybe. So let's have that O- take that H. Now we have an alcohol, which is fine, and we made OH-. But now we remember that heat. 6, 5, 4, 3, 2, 1. That heat makes me think that OH- might be a good leaving group, or we might make a pi bond, right? Do an elimination. But which carbon has the CH that I'm going to take? Don't forget your rules. To do an elimination, what hydrogens do you look at for eliminations? Which hydrogens? The beta hydrogens, right? And if you can make something conjugated, would you rather do that? Yes. And carbon 2 is carbon 2's. That's an alpha site, right? That's an alpha carbon, right? If this is the carbonyl, carbon 2 is alpha to it, and so is carbon 4. But why would I choose carbon 2 if it has a CH? Because then I can eliminate the OH. So if let's draw that H there. Because it still has an alpha CH. If it didn't have alpha CHs, could I do this? No, you'd be stuck, right? If there was no alpha CHs, can you deprotonate them? No.
Well, won't you just go on further?
You could, but then it wouldn't lead to anything. So here it comes. We'll do a little, what kind of reaction is this? An elimination E2. be a pi bond. There'd be OH minus as like a catalyst in this situation. We also generated water. Oh, there's still a carbon there. Let's number our carbons. 1, 2, 2. Close. 2, 3, 4, 5, 6. Right, we got a 5-member ring, and alpha beta unsaturated ketone is what we've just made. Good. So let's look at class notes again. Problem 5. The last one, actually 5 there. So we have, in this case, we already have, we have a dicarbonyl, which we know is more acidic. We also know from the first one, from 4, that what kind of nucleophile is a dicarbonyl enolate? When there's 2 carbonyls and they're sharing that charge, is that a soft nucleophile or a hard nucleophile? Soft, because of resonance, right? It's more stabilized. So soft nucleophiles always attack beta. Just something to think about. And we take a look at our electrophile. Right? Well, it's an alpha beta unsaturated ketone. So which carbon do we expect to attack? Well, let's number them. So let's make that 1, 2, 3, 4. Which carbon should we attack? Carbon 1 is the nucleophile. We can all agree on that, hopefully. Which carbon should we attack? 1, 2, 3, or 4? What kind of nucleophile is this? Hard or soft? It's stabilized by resonance, so it's soft. So it should attack the carbon that is not as delta plus. Which carbon is not as delta plus? 2, 3, or 4? 4, the beta carbon. Remember that? The beta carbon. Yep, so my funny looking negative charge then attacks carbon 4. The pi bond between 3 and 4 goes between 2 and 3. The electrons between 2 and the oxygen go up. Break the pi bond. So what do we have? So 1 is now bonded to 2. 2 is still bonded to 3. There's a pi bond there. We're still bonded to 4. Those other ones. 3, 4. Nope, I screwed this up, didn't I? Should we number our carbons right? That's good. That's why it's important. Did that on purpose. So carbon 1 is now bonded to carbon 4, which is bonded to 3, which has a pi bond to 2. And 2, of course, has an O minus now. And there's 2 other guys, and they just fit in. Right? So now we have this enolate. Right? What's going to happen here, the next step, they're saying, okay, well, we have a tetrahedral mediator and enolate. Are we going to, we're kind of stuck here, right? We're kind of done. Right? Normally, you'd have a base in there, right? You'd have water in there, and you'd reprotonate your enolate. So at this point, you're kind of done, and now we're going to add in H+, water, and heat. So now the question is, what is this all going to do? So we're okay with that conjugate addition. Should be done. No problems. Okay? So that next step, we have an enolate. How is an enolate going to react with acid? Well, electrons come down, pi bond attacks. Then reforms that enolate back into a ketone. Right? If you see H plus in an acid, there's usually a lot of H plus in water around. So now, if you look at the product, we made CO2, and it looks like the ester is gone, right? So how are we going to do that? Well, if you have H plus around and water, can you turn an ester into something else? What can you turn an ester into? The carboxylic acid. So let's do that maybe. So we activate it first. Yep, because there's more resonance, so that oxygen is actually more nucleophilic, but we're also trying to get rid of the ester, right? I kind of gave that clue to you when I showed you the product. So now we've activated the ester. Yippee. These other ketones are just kind of along for the ride. So now we've activated the ester. What can we do? The water can attack, right? And these are steps that you should already know. We did what? What did we just form? Tetrahedral intermediate. What's my best leaving group? The water, but we just added that, so we want to get rid of that. So when we do a proton transfer, we're going to do a proton transfer onto the part of the ester that we want to get rid of to turn it into a carboxylic acid. I'm just going to call the rest of this R at this point, just to save space. You can do that. I'm going to have one of these H's come down. We're going to make methanol. All right. The carboxylic acid and H+. Everybody with me to that point? Taking an ester and turning into a carboxylic acid. Hopefully we're all good there. Okay? Kind of shrinky-dink that over there. Oh, just a proton transfer. I should write that in. PT. Proton transfer. So let me draw what we have now, the whole molecule. We have everybody with me? We have the carboxylic acid now. So if we heat this up enough, we'll actually decarboxylate. So let me show you that mechanism. What's going to happen is, right, that OH bond is going to break. This CC bond is going to break. And we're going to make the enolate. But notice what we lost here. If I circled this in blue, what is that? That's CO2. We made H+, right? This H right here is this H. And we also made this enolate. Right? And if there's H+ around, what's going to happen right away with that enolate, do you think? It's going to grab it. And that gets you to the final product in your class notes. So you got to be careful when you have this ester, right? We have a dicarbonyl, and one of the carbonyls is an ester. They are prone to decarboxylate. So be careful with that. Okay, for number 11 on sapling, we have 2 aldehydes. That's the 2 up front represents. So when you see these cases like this, we have 2 of something. Usually one of them is going to be the nucleophile, one's going to be the electrophile, right? There's a reaction going to take place. And it says in here we have NaOH and water. That's fine. And it's 4 to 5 degrees. So NaOH, we should all recognize that's an ionic bond. So we have OH minus, which is a good base, and Na+. Good base, we should be looking for alpha CHs, right? So I'm going to go ahead and draw this aldehyde twice, because it says to draw it twice. I'm only going to deprotonate one of them. Only one of them will be the nucleophile. The other one will be the electrophile. H off here. I'm going to number my carbons. 1, 2, 3, 4, 5, 6, 7, 8. Right? I'm not going to draw that one there. All right. So the other thing I'm going to do. So now the base can attack. Make the enolate for one of these. All right, notice this aldehyde only had one type of. All right, aldehydes always only have one type of alpha CH. Right, they can only have one. Now this is going to attack. Let's number the carbons again. 1, 2, 3, 4. What is the best leaving group here? Is there a good leaving group? No. Right, there is no good leaving group. So we stop and say, well, we're done, right? So we have water around, right? Because we made water in this first step. We deprotonated right here. We made water. Now the oxygen can just come back, take that, and the final product is this aldol product I'm telling you about. One, two, three, four. OH. 5, 6, 7, 8. That's the aldol product, and you've also regenerated OH minus. Right, they'll do this a lot. There's another problem like this. I think number 12 is maybe similar to this. Now the difference between 12 and 13 in your homework is in those cases you can form more. You could actually form a conjugated system. So sometimes, right? Notice, are there any alpha CHs left here? There are no alpha CHs left. If there was an alpha CH left, and you heated it up, or it would form a pipe, like a conjugated system, you could take an alpha CH and do an E2 elimination. So look at 12 and 13 your homework for possibilities to do an E2 elimination, right? But this one, if there are no alpha CHs, can you take any? No. So be careful. Let's look at 5 in the class notes and the fourth problem in 5. That involved this enolate from this dicarbonyl. Right? This enolate from this dicarbonyl. Right? Now we got to ask ourselves what kind of nucleophile is this going to be? Is it going to be a hard nucleophile or a soft nucleophile? What kind? Hard or soft? Soft. Why would it be soft? But just because it has negative charge doesn't make it hard, right? Br minus has a negative charge, and that's soft. 2 oxygens are pulling on it. It has resonance structure 2 ways, so that makes it stable, right? Things that attack beta are more stable. The soft nucleophiles attack the soft position. Right? If it has resonance, or if it's big and fat and stable, it'll attack beta. All right? So which position are we going to attack? If I number this carbon here, 1, 2, 3, which carbon's going to get attacked? 1, 2, or 3? 3. Why? That's the beta position. Does the beta position feel the oxygen as much as carbon 1? So if you don't feel it as much, you are a soft electrophile, right? So this attacks carbon 3. Electrons go up. We should number our carbons. 1, 2, 3, 4, 5. So which bond is formed? Red 3 and blue 3 are forming a bond. All right. So I always like to draw the stuff that doesn't change first. What else is blue 3 bonded to? It's bonded to carbon 2. What's carbon 2 bonded to? Bonded to 1. Where's the new pi bond at?
1 and 2.
Between 1 and 2. 1 has an O minus also bonded to it, right? Electrons went up to the oxygen. And then the last 2 are the 5-mer ring. If I continue, this would be blue 4, blue 5, 4. Nope, 4, 5. Now we're kind of stuck here. We have an enolate, right? Actually, the last step then is H+, right? Do we have any good leaving groups at this point? Not really, right? So the final step is this electrons come down. Where's the enolate nucleophilic at? On the oxygen or carbon 1 or carbon 2? Which one? Where is this enolate right here? Where is it a good nucleophile? The oxygen, carbon 1, or carbon 2? It's not oxygen. It's carbon 2, right? The alpha carbon. And there's your final product. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Right? So these dicarbonyls attack beta. Right? These dicarbonyls attack beta. So number 14 in chapter 18. This involves two esters. So I'm going to draw them both out. Number 14, chapter 18. So same as we just did with the aldehydes. One's going to be the nucleophile, one's going to be an electrophile. We add in a ethoxide base. We have to add that in because if we use OH minus, right? OH minus could turn this ester into a carboxylic acid. So we have to be careful. Everybody, look at me. Pay attention. We're doing this, right? So I had to pick ethoxide. Otherwise, right, I would change the kind of ester I had. Right, so I had to pick this nucleophile or base. So what's it going to do? It's going to take an alpha CH. It's going to make an enolate. I'm going to draw this enolate like this time instead of the oxygen have a negative charge. No difference. Let's number some carbons. 1, 2, 3, 4, 5, 6, 7, 8. Which two carbons are going to react together? Which new bond is going to be formed between which two carbons? 8 and 3, right? So let's have 3 attack 8. Do the addition, right? We go from sp2 to sp3. So what do I know here? So 8 has an O minus. It still has, that's 8. It still has 7, 6, and 5. This oxygen's still on there. I have a new bond to 4, or to 3, which is bonded to 4, right? So let's see, 3, 4, what else was 3 bonded to? 2 and 1. Number your carbons. It's just going to be a pain otherwise. All right? The nucleophile electrolysis get too complicated. It's really hard if you don't number them. All right? So now we have a tetrahedral intermediate. What do we always ask ourselves when we have a tetrahedral intermediate? Are there any leaving groups? Are there any leaving groups here? Yes, there are, right? Esters, right, have leaving groups. They're from chapter 16. Chapter 16, remember, ester, amides, carboxylic acids, acid chlorides, anhydrides, those all had leaving groups. So these electrons come down and kick out that. So we end up with a ketone. Yep. You can't see it on the screen anymore. My bad. Let me erase this. Down here, I'll redraw it. Get a ketone. Make sure I number my carbons here, make sure I didn't miss anything. 5, 6, 7, 8, 3, 4, 2, 1. And I also have floating around, right? Balance my charge. The ethoxide floating around still, right? So am I done now? Now I'm done. Now the last step is H+. Well, the H+ is just for this guy to get protonated. That's all that's for. So your final product in this case is this. Right? So if you have an ester and you attack an ester, esters have leaving groups. So kick that leaving group out. And the second H+ is just to protonate that O- that you generated from breaking down the ester. So this is number 18 on chapter 18 sapling. So the first step is, let's see, you have this diester. Oh, it's 2 carbon there. And you have ethoxide, strong base. So what's it going to do? It's going to deprotonate this, right? In the spot between them. Takes the H, makes the enolate. Makes the enolate. Now we add in an electrophile. We add in the alkyl halide, that's the electrophile. Simple SN2 reaction. Plus Br minus. Everybody with me so far? No big deal? Let me shrink this down a little bit for me. Now what are we going to do with this? Now the next thing they say, we treat this with what? We treat it with OH minus and water. So OH minus, right, and water, OH minus can be a base, but it also could be a nucleophile. And you should remember from chapter 16, right, can we turn esters into carboxylic acids? Yes, we can. So what's going to happen, I'll show one version of it on this side. The OH minus actually attacks, right? It attacks there, makes a tetrahedral intermediate. And we're going to turn these two esters, what are we going to turn them both into? Does anybody know? What are we going to turn them both into? Not esters, we're going to turn them into carboxylic acids. All right, so I'm not going to do the other side, but you can believe me that it happens. Oops. I said believe me, so I might as well just do it. So I can turn both esters into carboxylic acids. That's what will happen. And now I have 2 ethoxide, OH minus is floating around, right? So now the third step at this point, let's put this over yonder. So overall we did an alkylation. Right, we made that carbon-carbon bond. We did a hydrolysis. Right, we turned the esters into carboxylic acids. We added water, essentially.
Okay, question on that
Yep.
one. So we learned in
Don't be careful, right? These are basic conditions. This is O minus,
but
so it's not acidic conditions. So we can't have water as a leaving group now. We can't have no plus charges. If you have O minus,
yeah,
no plus
but we
charges.
frequently had water, oxygen.
In acidic conditions, we did. Always in acidic.
Attack of carbon.
Water attack of carbon?
Yeah.
In acidic conditions, it could,
Okay.
right? Because then the electrophile would be good enough, right? You had to have acidic conditions.
Okay.
Yep. So now we're the dicarboxylic acid. We're going to add H3O plus and heat. So what are we going to do here? So H plus and water and heat. So these are forcing conditions. So let's have this carboxylic acid get protonated, even though that's very unlikely, right? But we're forcing conditions. All right, we're in heat, so high temp.
What's the leaving group on the last hydrolysis?
Still the ethoxide.
But there's an extra carbon in there.
They're all 2 carbon pieces.
No, but there's an extra carbon between the ether and the aldehyde. Do you see it?
There's
Neon?
Yep, it still makes. So I added an extra carbon in here. My bad. It would still make this enolate, right? Because that would still be the more acidic CH. So really, there should be. If I erase, that won't let me erase that now.
So
It should just be a big O here.
Okay. So it won't change the carbon formation.
Doesn't change anything. Yep, doesn't change anything else.
Okay.
So now we've protonated there. So now what's going to happen is we're actually going to lose CO2. So ready to watch these arrows. Here we go. I'm going to take this and regenerate H plus. This carbon-carbon bond is going to break and go right there. Now why would it want to do that? right? Well, what you're going to make here so I put a negative charge there. I made H plus, and I also made CO2 that was protonated as well. So at this point, this minus charge, right? Why would we make a minus charge at the alpha position? Why is that okay to make a negative charge at the alpha position? Why is that okay? Can you do resonance?
Resonance?
You can do resonance.
You're missing a couple carbons.
Oh. There you go. So that negative charge then is just going to immediately grab one of these H pluses. CO2 is going to go away, right? This H plus is going to go back to this carbon. You're going to make CO2, which will go away. You're going to make the carboxylic acid there, and you'll still have H plus floating around. Right? So this is a little tricky. This is hydrolysis under acidic conditions, how this would work.